un puente angosto, cómo el aprendizaje a temprana edad potencia o limita el desarrollo de sistemas de percepción. Lisa ha trabajado, tiene una trayectoria bastante larga, a pesar de que es bien joven, en este tema. Ella hizo un doctorado en psicología infantil en la Universidad de Minnesota. Tanto hizo un pregrado y el doctorado, donde trabajó con Charles Nelson, y trabajó fundamentalmente en aprendizaje visual temprano. Posteriormente se fue a hacer un postdoctorado a la Universidad de Colorado, donde trabajó con Tim Curran en aprendizaje visual también, pero en adultos.
Thank you very much, Maria de la Luz, for your introduction. It was very nice. And thank you also for inviting me here. My husband and I have had a wonderful time here in Chile. We came a week ago yesterday and have traveled to Viña del Mar and Valparaiso and traveled around Santiago, and we've had a wonderful time. I've really enjoyed my stay. So today I'm going to talk to you about some of the work that I've done related to infant perceptual learning and the role of early experience. So I know that a lot of you are interested in education and formal education, and I'm going to talk to you today about some things that are really important that are happening during early development in the first year of life. Too loud? Sorry. So, the basic architecture of the brain is constructed through an ongoing process that begins before birth and continues into adulthood. And I like to draw an analogy to buildings that are being built. And I understand that this is a controversial building, but nonetheless, it was, I think, a striking image of an analogy that I'd like to draw to building a brain early in development. So the early years of life matter because early experience affects the architecture of the maturing brain. And this architecture sets the foundation for later learning. So here in Chile, it's very important to have a very sturdy architecture and to follow various codes related to building buildings because of the chance that you have earthquakes here. And so you invest a lot of money and a lot of time into building a strong foundation that can withstand those kinds of problems. And I'd like you to think about that as an analogy to how we should be building a brain during development. So early experience influences brain architecture and function. So you can see here at the bottom of the screen, these are just some cartoons of some neural connections, and you have an image here of a baby who's learning to crawl and learning to balance and forming some connections. And then here you have an expert, your Chilean Olympic gymnast, Tomas Gonzalez, who has obviously gone beyond the simple balance and learning to move and walk, which the baby is learning, and form some extra connections here in the motor cortex and in the visual cortex and all over the brain to be able to do some of the amazing things that he did just a few weeks ago. So how do babies learn about the surrounding environment? How do they learn to recognize and identify people and objects? So my area of expertise is primarily in perception, and I'm interested in trying to understand how babies learn to perceive and recognize people and objects in the world. And I use face perception as a model system for learning, and I think that it's a very good system for understanding how learning in early development works. Number one, because babies really like to look at faces. They are constantly orienting towards faces, and they will sit and look at faces for a long period of time, so we can do all sorts of things, like record brain activity and show them many, many pictures, all of which I'll explain to you in a little bit. But faces also carry critical information about the world around you. And in order to successfully navigate the world, it's often very important for you to glean information from faces. So when you look at a face from a very single fixation, you can make inferences about intentions. You can make inferences about age and emotion. So if I keep looking back to this door, you may then redirect your attention towards that door because you see that I keep directing my attention over there. So you're using the information in my face to try and figure out what I'm looking at the door. Or if I all of a sudden was up here, all of you are facing me, and I looked very scared, it's probably likely that you'll all turn around to try and figure out what I'm looking at that's scary. So you're using that information in my face to sort of orient your own orientation to the world. You can also glean information about race and attractiveness, identity. A lot of times you'll be walking around and you may run into somebody outside of the context that you would typically see them in, and you know that you recognize that person, but you can't quite remember their name or where you know them from. And so that's sort of all this information is information that you glean from recognizing faces. So I'm going to show you a couple pictures here. Because we all are very good at recognizing faces, and many people have hypothesized that we are all perceptual experts. So similar to a bird expert being able to recognize and identify different species of birds, we're all very good at recognizing and identifying faces. And we also have biases within this system. So I'm going to show you a picture of a monkey face. And I want you to tell me if this picture is the same monkey as that picture or a different one. Same? Different? So it was a different monkey. They're two different monkeys. And so it's just an illustration of how, if I show you faces that you don't have a lot of experience discriminating, you're not very good at matching those faces or identifying those faces. You're not as good as you would be if I showed you pictures of people with the monkey face than the monkey faces. So there are several biases in face perception that have been studied around the world. The species bias has been studied quite extensively, and primarily people study the other species effect because we know that most humans don't have a lot of experience recognizing and identifying monkeys. So that's one of the reasons that system has been, or that stimulus has been used quite a bit. But people also study faces of other races, and that's been widely studied around the world, and there's a robust finding that you're much better at recognizing and identifying people of your own race than of a different race, unless you were raised in an environment or surrounded by people of a different race. You're also better at recognizing people who are of your own age or an age that you have previously experienced than people of a different age. And there are also gender effects that occur in infancy. So 6-month-olds are better at differentiating females if they're primarily raised by their mother, and they're better at differentiating males if they're primarily raised by their father. So all of these biases in face recognition lead to or are influenced by the experience that infants have in their environment. And one of the mechanisms for developing these biases has been studied, is called perceptual narrowing. And so this is an analogy that I like to draw to the development of these perceptual systems. So if you have this bridge here, and you think about early development as starting right at the beginning of that bridge, you have this sort of more broad area in the brain that is ready for the kinds of experiences that the world is going to offer. And then with those experiences, you begin to narrow your perceptual system to be responsive to the things that you see in your environment. So if you don't see monkey faces in your environment, it's probably not that important for you to be able to tell the difference between two different monkey faces. And so you're not going to strengthen those neural connections. Instead, you're going to strengthen neural connections for the kinds of faces that you see in your environment. So lots of work has been done that suggests that 6-month-olds can differentiate among faces within other races and other species that neither 9-month-olds nor adults can differentiate. And this decline is based in environmental input or a lack of environmental input. And this is very similar to what happens in language development. So in language development, early on, infants can discriminate among sounds of many languages, and then with development, by 9 to 12 months of age, they begin to focus on the language that's present in their environment, and they decline in their ability to distinguish sounds that are not present in their native language. So one of the first studies to look at perceptual narrowing was done by Olivier Piscalis, Michel Dehaene, and Charles Nelson in 2002. And they found that when discriminating human faces, 6-month-olds, 9-month-olds, and adults all readily discriminated human faces. But when discriminating monkey faces, only the 6-month-olds showed discrimination of those faces, suggesting that by 9 months of age, infants are already beginning to learn that it is not a part of their, it's not important for them to recognize the difference between these monkey faces. And when they're 6 months, they haven't quite learned that. So we've identified this period between 6 and 9 months of age that seems to be very important for building a foundation for face perception. In the work that I've done in the last few years, I've tried to focus on answering this question. So many people have identified that perceptual narrowing exists, but what hasn't been identified is what's narrowing, what are the mechanisms that are changing during the first year of life, and what kinds of things can we do to enhance or constrain learning. So much of the work that I've done has also drawn from the adult literature on perceptual expertise. And adults typically process objects and faces at different levels. So if I show you this face and assume that you're all familiar with this person, your entry level of processing or identifying this individual is at the individual level. So you would be faster at identifying this as Tomas Gonzalez than saying that it's a man, a human, or a living thing. However, if I showed you a picture of a bird, you would be, typically, unless you're a bird expert, you would identify this as a bird. So you're identifying this object at a different level of processing. But if you were a bird expert, you may identify that image as an American tree sparrow. Or if you had a pet bird, you may have a name for that particular bird. And so one of the things that I was interested in trying to figure out was whether we learn faces early in development at a different level than we learn objects. And studies of adult perceptual expertise, some of the work that I've done prior to doing some of these developmental studies, I looked at what happens when we train adults to identify pictures of birds or cars, and we've consistently found that subordinate level or individual level training relative to category or exposure training with objects or faces leads to the increased ability to tell the difference between exemplars within a category. greater holistic processing of trained stimuli. So instead of focusing on identifying the features, like the color of the beak or the length of the beak, you would process that image, if you were a bird expert, more holistically, very similar to how we process faces. And previous studies have also found more specialized neural responses for trained categories. So the first study that I'm going to talk to you about, my goal was to try and answer this question. Does learning to associate an individual level label with a face during infancy lead to different behavioral and neural representations than learning a category level label? And the second question that I'm going to talk to you about is whether the period from 6 to 9 months of age is an important time for building a perceptual foundation. Is this, or could this be considered a sensitive period for face perception? But before I get started, I want to just briefly go over some of the methods that we use in my laboratory. So we use both behavioral measures and electrophysiological measures. And so for some of you that may not have studied infants before, you may wonder how we measure behavior, because they're not very good at telling us what they know or pressing buttons. So what we focused on primarily is looking time measures, and we've also just recently purchased an eye tracker where we can more precisely look at the pattern of visual fixation and the duration of visual fixation when they're looking at faces and objects. And we also record event-related potentials. And I'll go through each of those methods very briefly just to give you an idea before I present the data. So in this image here, we have an infant that's typically sitting on the mother's lap or the father's lap. We have a little camera here that records the infant's face, and we get an image that looks like that. And then we present the infant typically with paired images. And we record which picture the infant looks at, and we record how long they look at that picture. And so if they look at one picture longer than another picture, it may indicate that they can tell the difference between those two pictures, or that they're more interested in one picture versus another picture. And then we get a recording that looks something like this. And we can slow this recording down quite a bit, and several students in my lab spend hours and hours and hours coding the videos and coding the duration of looking to each of the images on the screen. So you can imagine that this is very time-consuming. Now that we have an eye tracker, we can just calculate this, and you don't have to code the videos, which makes it much easier. So we also record event-related potentials, and event-related potentials is basically a recording of EEG, time-locked to a stimulus presentation. And when we record EEG, this is an image of a neuron here. So neurons produce tiny electrical fields, and when you get a lot of these neurons that are aligned within a region of cortex, so this is a region of folded cortex here, you produce summed electrical fields, which we can measure in EEG. So when we're measuring EEG, we're not actually measuring action potentials. We're measuring the postsynaptic potentials, or the change in the cellular space that occurs when a group of neurons are activated. And when you have this folded region of cortex within the brain, we can put electrodes on the head and record positive and negative deflections that are occurring in response to images. So here you have a picture of an infant with a net on. We have a system that has 128 electrodes, and typically what we do is we show infants pictures on a computer screen while we have this net on their head, which is plugged into an amplifier. Baby's brain activity is very tiny, and so we have to amplify it in order to look at it. And that produces an EEG, or just the ongoing brain activity. And then what we do is we present these pictures. So in this case, we might present, for example, a picture of the mother's face and a picture of a stranger's face. And we'd present the picture of a mother's face 50 times and the picture of a stranger's face 50 times. And then we can mark in the ongoing EEG where the onset of the mother's face and the onset of the stranger's face occurred, and then we average across those presentations. And when we do that, we get what's called the event-related potential, or a specific brain response that is specifically in response to the picture of either the mother or the stranger. And then we can look at these peaks, the negative and the positive peaks. We can look at the amplitude response. So let's say for one condition you might get a larger response to the mother's face than a stranger's face, and we can calculate that difference. You might also get a later response, so it might occur just a few milliseconds after the response to the mother's face, and we can record how fast these responses are occurring in the brain. So this is what a typical infant ERP component might look like, and I'm going to show you a few of these. So I'm going to take some time to go over that. So we typically record a baseline from 100, about -100 to 0, where we have no pictures, and we can compare the rest of what's going on to that baseline activity. Then we have the presentation of a face or an object for 500 milliseconds. And then you'll get a response to that face or object. This is milliseconds here and microvolts here. And you get, the components are named by the latency of the components or the number of the peak and whether it's a positive or negative peak. So here this is a positive peak, so it's the first peak, so it's often called the P1. This is the N290 because it occurs around 290 milliseconds after the picture comes on, and it's a negative peak, a negative going deflection. And then this is the P400 component, which is also a positive component occurring around 400 milliseconds. And all of these are recorded over the back of the head. So if this is the nose up here and the ears down here, this is the region over the occipital and temporal regions of the brain. And we can record the responses, and these are typical responses when an infant sees a face or an object. And I'll show you a quick video, because oftentimes people wonder how we do this, how we get babies to wear the nets, which is somewhat challenging. But we typically have the infant sit on the mother's lap, and we have one researcher that stands behind. And we sneak up behind them. Sometimes they get a little bit miffed, but usually we can distract them with a few toys. 6-month-olds are actually very easy to test. They don't have a lot of motor control over their hands. Once you get to test 12-month-olds, they can just rip the net right off. So the ERP technique can tell us processes not detected or masked by behavior. So oftentimes when you're pressing a button in response to a task, there's a lot of different neural things that have to happen in your brain in order for you to press that button. And sometimes with ERPs, we can look at the different stages of what's happening before you press that button and try and isolate different processes in cognition and perception. It gives us extensive temporal information about brain processes. It's an additional level of analysis, so in addition to behavior, we can record brain activity, and if we get very similar results, we can feel more confident in our conclusions, but also sometimes you get diverging evidence, and that what happens in the brain is very different than what's happening in behavior, and it may cause you to reformulate your hypotheses about what might be going on. And you can study many different populations using this technique. You can compare infants and children, adults, elderly populations, and many clinical populations. So it's a very useful technique in that sense. So going back to the question, does learning associate an individual level label, learning to associate an individual level label with a face during infancy lead to different behavioral and neural representations than learning a category level label? So what we did is we had a training design. We brought infants into the lab when they were 6-month-olds, and we recorded their brain activity and their behavioral response prior to any training. And then we sent them home with a picture book, one of 2 picture books that I'll show you in just a minute. And then we brought them back at 9 months of age and did the same exact behavioral and ERP testing that we did at 6 months of age. So we asked parents to read a book to them that contained 6 pictures of monkey faces. And in one group, they received an individual level label. Dario, Boris, Anis, Carlos, Flora, Luis. And in the other group, they received a category level label where all of the faces were all the same, but the label, the faces were all the same as the individual group, but the label was just monkey, 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 monkey for all of the images. For the looking time measures, we looked at whether infants could discriminate among the monkey faces. So we familiarized them to a single monkey face. So these were monkey faces that were not trained in the book. So we trained them on 6 monkey faces, and then they were tested on brand new monkey faces that they had never seen before. So we're testing generalization of learning, not just what they remembered from the book. And we familiarized them to a single face for 30 seconds. So we basically showed them a face until they were completely bored with that face and they were looking at anything else but that face. And then we paired that familiar face with a new face. And so if infants discriminate the 2 faces, they will look longer at the new face because they're already bored with that face. And then we switch sides because some infants just like to look at one side of the screen all the time and tend to make us think that they can discriminate, but really they just like to look at one side of the screen. So switching sides allows us to control for that. For the ERP task, we showed infants upright and inverted monkey faces. So we wanted to determine whether infants were forming a holistic representation of faces. Response to inverted faces than upright faces. And so I wanted to determine whether this kind of training might induce a holistic representation of these monkey faces. So the results that we have, so here you can see this is % looking to the novel stimulus. And you have category level training where they just saw all of the same, they had all the same names. And individual level training where all of the monkeys had different names. And prior to training, you can see at 6 months, we replicate previous studies that have found that infants can discriminate the monkey faces at 6 months. But at 9 months of age, after the training at the category level, they declined or lost the ability to discriminate those monkey faces. But with individual level training, they maintained their ability to discriminate those faces. So that individual level training seems to keep them able to tell the difference between those faces, just like you would maintain the ability to tell the difference between the faces of your family members and the people that are in your environment. In the ERP response, again, we recorded in response to upright and inverted monkey faces that they've never seen before. And this is pre-training here. You can see there are no differences. The gray line is the upright and the black line is inverted. And there are no differences significant differences between upright and inverted at pre-training, and this is for the category level training. So with all the faces labeled monkey, and at post-training, there was no difference between upright and inverted faces. But for individual level training, again, pre-training there was no differences, significant differences, but at post-training we got a significant difference that started at this N290 component and continued on to the P400 component, and it was greater for inverted than upright faces, suggesting that the training that we did for 3 months from 6 to 9 months of age seems to lead infants to process these faces more holistically, and so when we invert a face, they're more disrupted in their processing of these faces. And finally, this is just a different way to look at this, the data. This is the back of the head, and you can see that the response here in the back of the head, this difference between the individual upright minus inverted for the individual post-training is concentrated in the back of the head in occipital temporal regions that are also typically where we find adult face processing. So experience learning to associate an individual level label with a monkey face from 6 to 9 months of age leads infants to form a different neural architecture which allows them to tell the difference between monkey faces. It likely involves an increase in holistic processing, and category level training leads infants to group the faces together, making it more difficult to distinguish individuals, and neural response does not change with category level training. So the labels that we are giving the infants from 6 to 9 months of age prior to the onset of any production in language seems to be very important in their conceptual development. And so another analogy that I like to give to try and explain this to parents is that with regard to perception, all infants start out at the same place. Then depending on the demands of their environment, they maintain and strengthen neural connections needed for more specific representations for some categories than others. And so the example that I give is when parents are labeling dogs. So if you live in a neighborhood or an area where you have a dog and your neighbors have dogs, the labels that you might give those dogs might be Susie or Oliver or Spot. And you give those dogs individual level labels, which may lead infants and children to be able to tell the difference between those dogs. And it might be important for them to tell the difference between those dogs because maybe one of those dogs is a familiar, friendly dog and maybe another one is not. But if you grow up or you live in an area where there aren't any dogs, when you see dogs, the parents might say, oh, there's a dog, another dog, and they might call them all dogs, and then you're forming a different concept of dogs where it's not important to tell the difference between individual dogs, but in this case, it's more important to group those together into a single category. So what seems to be happening is that we are extending these neural connections to include an individual level label that may also induce holistic processing. So one of the questions that we've recently been trying to answer is whether this training related to change is a long-lasting one. So the training that we did from 6 to 9 months of age, how long-lasting is this, and is this period considered a sensitive period for face learning? So we've recently conducted a follow-up study where we brought children back in who participated in the monkey face training study from 6 to 9 months of age, and we brought them back when they're 5 to 6 years of age. And when the infants came back into the lab, they all brought the books back, and so presumably after 9 months of age, they have not had any more experience with the monkey face books that we gave them or those monkey faces that they saw. So we aimed to determine whether or not the 3 months of experience with the monkey faces had any long-lasting effects on behavior or on their neural responses. And similar to the visual paired comparison task, we used a delayed match to sample task for these kids, where they saw an image of a monkey face. They were asked to press the button when they feel that they had learned the face, when they'd memorized the face. Then there was a 5-second delay, and then we had a test trial where we asked them to press the button to the face that corresponds to the familiar face, to the face that they just saw. And we used both monkey faces. Again, these monkey faces were not faces that were trained in the book. They're brand new faces. And we had a control group, or a control condition where they saw human faces. We also had them complete an ERP task where they saw upright and inverted monkey faces, and they had, again, new monkey faces and control faces. This was in the context of a Finding Nemo task. So we showed these upright and inverted faces, but we told the kids that every time they saw Nemo, they needed to press a button, and then they were given a sticker of Nemo that they could put into a sticker book later. And it was very important for us to have this be a fun task, because you can imagine that 5- and 6-year-olds were not very interested in sitting through 100 pictures or 200 pictures of upright and inverted humans and monkeys. So we added that task in there to make sure that they were continuing to pay attention and engaged in the task. So our behavioral results, and remember, these kids are now 5 to 6 years of age, and we did not find any differences in response to percent correct. All of the kids performed very well on this task, but in response to the human faces, we have the individual level training, the category level training, and a control group. The control group had no training prior to coming into the lab. I want to point out here that because this is a longitudinal follow-up, we have low numbers of subjects right now. We're continuing to collect this data and hoping to get these numbers up. But the response to the human faces, if you were trained at the individual level, you were significantly faster at indicating that the face was a familiar face than if you were trained at the category level, and then if you were trained, if you were in the control group and you received no training. So this is with human faces. The individual level training is at 5 years of age leads these kids to be significantly faster at this task with human faces and with monkey faces. In the monkey face condition, the individual level training was significantly different from the category level training, but was only marginally different than the control training. So what this suggests is that the training that we did from 6 to 9 months of age is actually influencing their behavioral responses and the reaction time in this task almost 5 years later. And it does seem to transfer to human faces. So the training that we did from 6 to 9 months of age didn't include any human faces. One of my hypotheses about what might be going on here is that once we've stopped training at the individual level, the kinds of faces that they continue to individuate tend to be human faces. So we're almost giving them a little bit of a jump start on individuation from 6 to 9 months of age, and they continue to use the information that they learned from these books and that the parents are reading to them and labeling things in their environment to apply that learning to the category that they continue to process, which is human faces. The other difference, looking at the regional brain responses, so these again are images of the back of the head, what's going on in occipital and temporal regions, and these are difference responses. So this is the individual level training group. compared to this huge difference there. So this is a much more specific and concentrated region that is often involved in expert face processing. And these are the responses averaged across the human and the monkey faces, because we didn't find many behavioral differences there. And so in the individual level group, they have a much more specific response or difference between those two than the control group. And here, the category level group and the control group here, the difference is much more widespread. It's not quite as specific, and it's a little bit more varied. So there's more variation here than there. So not only does it lead to different behavioral effects, but it also seems to lead to a difference in the specificity of the neural response. So, to conclude, explicit individual level training between 6 and 9 months of age may facilitate individual level learning and processing at 5 to 6 years of age. Individual level experience past 9 months of age consists of human faces, thus sensitivity to individual level learning and processing may be applied to human faces. A lack of direct competition from monkey faces or any other expert category may lead to face perception facilitation effects. So the experience from 6 to 9 months of age may facilitate later learning. In terms of the questions that I posed earlier, does learning to associate an individual level label with a face during infancy lead to different behavioral and neural responses and representations than learning a category level label? It does seem that individual level labeling prior to the onset of verbal communication is important and leads to better discrimination and specialized neural responses. So it influences their conceptual development of the world around them. And is the period between 6 and 9 months of age important? It seems that early experience enhances reaction time and influences the specificity of the brain response, but the next step is actually to try and do the training between maybe 9 and 12 months of age and see if we get the same kind of effects that we got, because we're not quite clear that this period per se is very important. It could be that this kind of learning could happen at any time. So we still have to do more work to try and sort of understand that period, if it's a very important period, or if we can just start training when they're 4 years of age and then benefit later learning. Some implications for education and policy on this work. The early years of life are important because experiences affect the architecture of the maturing brain. Thus, the architecture sets the foundation for later learning, and these foundations are sometimes built before the onset of formal education. And so, in my view, I think we need to invest resources into educating parents about early learning and about the importance of talking to their infants, even though the infants can't talk back. So those are some of my take-home messages. I think conceptual learning occurs much earlier than parents often perceive it to occur. So I want to thank all of the infants, families, and children that participated in this study, and several of the funding sources for this work that have been extremely helpful, and my wonderful lab. This is my lab group from 2011, and this is more recently a picture of the lab group. And without them, I would not have been able to do this work. They're very creative and hardworking group of individuals. So thank you, and thank you for listening.
Significativos en el desarrollo futuro del niño. La pregunta mía va en lo siguiente. De acuerdo a esta investigación, ¿podría pensarse que la estimulación a esta corta edad de los niños a través de imágenes que vayan desarrollando una percepción de la realidad distinta, como por ejemplo, en vez de colocar un individuo, colocar un colectivo, en vez de colocar animar varios animales para, por ejemplo, agregar a su concepción de principio que la persona no vive sola, sino que vive en un contexto social, el cual es parte de su desarrollo y su vida, y eso quedara implícitamente grabado para el resto de su vida? Esa es mi pregunta.
Vamos a tomar varias preguntas. ¿Más preguntas? Allá. Okay.
Hola. Quería saber si estos estudios los habían traspolado para niños con trastornos de comunicación como Asperger, autismo, Red, y de ser así, si este tipo de estudios puede ser predictores como diagnósticos para este tipo de trastornos e inclusive como tratamiento o entrenamiento para ellos.
Atrás hay dos personas.
Gracias por poder asistir a tu hermosa presentación. Te agradezco enormemente. Y la pregunta es, en Oriente se hizo un estudio en 1987 con respecto al aprendizaje a partir de una similitud de experiencia como la que tú estás presentando. En esa ocasión se desarrollaron metodologías de aprendizaje y la fundamentación, y es la pregunta que te hago, ¿no es cierto?, es que el niño capta una imagen en 2 segundos. Estamos hablando de que en Oriente se hizo el estudio con la población oriental. ¿Has hecho algún estudio con respecto a el periodo en que un niño capta una imagen? Eso. Y lo segundo, agradecerte la imagen de Tomás González. En tu exposición tuve la suerte de trabajar en Neurociencias, con quien le acompañó, que fue Simona Castro, que por primera vez integra la selección chilena de gimnasia a tu país en los Juegos Olímpicos.
¿Más preguntas? Cortita, ¿hay alguien que tenga otra?
En este momento la educación tiene una problemática, digamos, de ubicación temporoespacial. Las salas de clases son piramidales. El profesor está adelante y los chicos están sentados tal cuales estamos nosotros ahora. Y cuando hablamos de percepción angosta, ese es un problema, digamos, para captar dentro del entorno aprendizaje, porque hay una interrelación que son el resto de los niños. En la pedagogía holística la tendencia es la formación circular. ¿Qué opinas al respecto?
Ya. ¿Más preguntas? No. Ok.
Okay, very good questions. I have a very poor memory, so if I miss something, please let me know, and I can try and let me know if I miss something, please. So the very first question, talking about meaningful images and early perception, and whether we should be showing our infants a collection of images as opposed to groups of images. And I think it's a difficult question because it may not be important. Like I was saying with the monkey faces, it may not be important for infants to be able to tell the difference between 2 monkey faces. So in that view, I'm not sure that showing a collection of images in the hopes of having them be able to better discriminate 2 different monkeys is that important, because they may not use that skill in their lives. But it may be important for them to identify and differentiate faces of other races. And so I think a lot more work needs to be done to try and, I guess, better apply some of these results to parenting practices. So I'm not, at this point in time, I don't think this work is ready to start to sell books or sell flashcards or any of those other kinds of things. I think at this time it's just sort of highlighting the importance of how infants learn from the labels that are provided to them, and that parents should be labeling their environment, and they should do so naturally, and try and label things that are important for the infants to understand, and realize that the infants are learning quite a bit during this period of time. The next question, I think, was a very important question that I get quite often about communication disorders and early autism. It is something that I think is very promising for understanding autism. As a lot of you probably know, kids with autism have deficits in recognizing and identifying faces. They also have deficits in using face information for social navigation of the world. And they tend to process faces in a more featural manner than a holistic manner. And so a lot of those deficits are things that I've highlighted here. And I think that it may be a very important tool for identifying individuals who have autism at an earlier age. The problem is it's very difficult at this point in time to identify populations of infants who are at risk for autism and study them from 6 to 9 months of age. You have to study hundreds and hundreds of infants and follow them over time to the age of diagnosis, which is often at earliest 2 or 3 years of age. So it's very difficult. There are some people. My former advisor, Charles Nelson, has been studying infant siblings of kids who have autism and trying to identify that. But even those siblings tend to, the rate of getting autism is I think it's only 10%. So they're not at that much of a higher risk of getting autism than if they didn't have an infant sibling. So I think it's a very important question, and it may be very useful, but I think we need to you need to get a lot of money to be able to do that kind of work and to be able to follow those kids over time. The next question, I think, had to do with the timing of how long it takes an infant to learn an image. And I think it's a very important question, and one of the things that we do in our lab is we tend to do pilot testing to see how long it takes infants to familiarize to a certain image. And it differs depending on the kind of image that they're looking at. So if we show them a picture of an object, they get bored much faster than if we show them a picture of a face. And so I think some of that, the question about timing, has to do with the type of image that you're showing them and how interested they are in that image. But I'm not sure that I'm familiar or remember the study that you cited that found that 2 seconds was enough time. We do show the images in the ERP task for 500 milliseconds, and we know that they are differentiating those images, so I think that 2 seconds would be plenty of time for the infants. What information that they glean from that image within 2 seconds is a different question. But I do think it's enough time for them to identify whether it's a face and identify whether it's a familiar stimulus to them. And the last question, I'm not sure that I have the expertise to answer the question about the spatial or temporal layout of the classrooms. I'm sorry, I don't think that I know enough about that area to be able to even give a hypothesis about what would be a better way to learn in the classroom. Primarily, I think because what I study is in infants. I do think that infants learn a lot from one-on-one interactions with the parents, and I think that that's very important. And so presumably smaller classrooms and more interaction would probably be better. But again, that's not exactly not my area of expertise, so I don't feel too comfortable making any strong claims about it. It's a good question.